Hello, my people. I hope we're doing well. Um, this will be the first of several videos for right triangle trigonometry for day 3 of our summer trig. So far, we've gone over what I referred to as pre-trigonometry, where we talked about radians and degrees and the conversion between them, and we talked about arc length and linear speed and angular speed, and we sort of just sort of played around with those quantities a little bit in order to gain a little bit more facility with them. And then on day 2 we move forward and put one foot into the world of trig in constructing the unit circle so that we have a memorization tool for understanding not only how we get the values that we get, but a way of memorizing them so that they're sort of on the tip of our tongue when we need them. Okay. And just by way of review, I've sort of just laid out here the right triangle definitions. We have sine as opposite over hypotenuse, cosine as adjacent over hypotenuse, and tangent as opposite over adjacent, with the SOHCAHTOA that you probably memorized back in geometry. But in pre-cal, we add to those 3 more, which wind up being the reciprocals of the 3 that you learned back in geometry. We have cosecant, which is hypotenuse over opposite, being the reciprocal of sine. We have secant, being hypotenuse over adjacent, which is the reciprocal of cosine. And cotangent, which is adjacent over opposite, being the reciprocal of tangent. Not only do we add these 3, but then we take the trigonometry and oftentimes anchor it within the Cartesian plane so that we can sort of use our analytic geometry skills to evaluate some of these things. Okay. So let's go ahead and in this section we will be doing some practice problems, but right now I want to cover a couple of things that are being introduced in this section. And one of them is they explicitly introduced even odd identities, although those were touched upon in the last section. What we should see is cosine and secant, and I've divided them like this because these two are our only even ones, okay? And by even, we mean that if we're looking at it graphically, that it has y-axis symmetry. And so basically, if we have, cosine of negative pi over 6, that's going to be equal to root 3 over 2, and that's also equal to cosine of positive pi over 6. Okay? And the same sort of thing happens for secant. And we'll see this y-axis symmetry when we actually get to those graphs. And we'll see cosine and secant basically being split right down the middle by that y-axis. When we get down to the last 4, we recognize the fact that these are odd, meaning that if I have sine of negative pi over 6, okay, that's going to be negative 1/2, which is negative sine of pi over 6. And I'm just using pi over 6 as an example. It could be anything, right? You could do cosine of negative 3 pi over 4. Cosine of negative 3 pi over 4. Now, negative 3 pi over 4 is coterminal with 5 pi over 4. We know, because it has a reference angle of pi over 4, that it's going to be either root 2 over 2 or negative root 2 over 2. But negative 3 pi over 4 is in quadrant 3. Quadrant 3 is to the left of the y-axis, giving us negative x values, and therefore giving us negative cosine values. And you're going to get negative root 2 over 2. But that's equal to cosine of 3 pi over 4, because cosine of 3 pi over 4 is in the second quadrant, which also gives us negative values. okay? And so if we apply that same thing to sine down here, sine of negative 3 pi over 4, also is going to be negative root 2 over 2 because negative 3 pi over 4 is in the third quadrant, both x and y are negative, and therefore both the cosine and the sine are negative. But we recognize the fact that sine of positive 3 pi over 4 is going to be in the second quadrant, and there sine is positive, so it's basically the sine of negative theta is equal to the negative sine of theta. And as we see when we get to the graphs of sine and tangent and cosecant and cotangent, we will see that origin symmetry, and I'll bring it back around. The benefit for us here is we're going to actually be using some of these identities to evaluate some of the trigonometric ratios. And of course, we'll confirm that by actually, anchoring them in a triangle and all sorts of fun stuff like that. But I want you to see how these actually can be used, not only for the purposes that we will use them for when we get to chapter 5, which is referred to as analytic trigonometry, but they also help us to evaluate at times. Okay, and the same thing is true for these, which are called Pythagorean identities. And you're thinking to yourself, gosh, why in the world do they call them that? I am so happy that you asked, okay? Because I am here to explain that. Let's say that we just want to use the Pythagorean theorem in order to represent the sides of those triangles. And I know it's bad form, but I'm just going to use O for opposite. I know it can get confused with 0, but since we're not actually going to be doing anything with a significant amount of numbers, it's fine for right now. So I see the fact that its opposite squared plus adjacent squared is equal to hypotenuse squared. Now, I don't know if you knew this about me, but I love division. Division is my favorite. It's like my favoriteest thing in the entire world. So let's go ahead and play around with this, and let's divide both sides by h squared. Does that sound good? I think that sounds fantastic. Now, using rules of exponents, I actually can change these into that. Oh my gosh, well, opposite over hypotenuse, gosh, that's sine, right? And adjacent over hypotenuse, well, that's cosine. And then we'll use lazy man's notation and get rid of those parentheses and pop the squared in between the trig function and the theta, and we get our first Pythagorean identity. And of course, that Pythagorean identity has 3 different forms, right? Because it can be written as sine squared theta is equal to 1 minus cosine squared theta, and it can also be written as cosine squared theta is equal to 1 minus sine squared theta. Now, both of those are going to come in they're going to be a little bit more useful in the next chapter, but I at least wanted to go ahead and give you a heads up. Okay, well, I'm not done yet. I have sine squared theta plus cosine squared theta is equal to 1, but I've told you division is my favoriteest in the entire world. So what do you say we go ahead and take this one and see what happens when we divide through by sine squared? Okay, well, sine squared over sine squared, well, that's going to be 1. Cosine squared over sine squared, that's the same thing as cosine over sine, the whole thing squared. So that's cotangent squared. And that's equal to the same thing as 1 over sine theta, the whole thing squared. So that's going to be cosecant squared. Oh my gosh, will you look at that. That is that one right there. Wow, that's neato. Okay, so let's go ahead and put a box around that bad boy. And then, of course, we want to recognize the fact that, cosecant squared theta minus cotangent squared theta is equal to 1. That's another form of that one. And, of course, we can have cotangent squared theta is equal to cosecant squared theta minus 1. And just like the last batch of the ones that are turned into a difference, those are going to be a little bit more helpful in the next sort of unit, analytic trig. But I'm still not done. Let's go back to that sine squared theta plus cosine squared theta is equal to 1. And let's divide again, because like I said, it's totally my favorite. And let's divide this time by cosine squared. And this one is going to be sine squared over cosine squared. Well, that's the same thing using rules of exponents as sine over cosine, the whole thing squared. And that means that that's tangent squared. Well, that's something over itself, so that's 1. And this is 1 over cosine, the whole thing squared. And that's going to be secant squared theta. Oh my gosh, will you look at that? That is that one. Fantastic. And of course, just like the last two, it has other forms. We can, of course, subtract 1 from both sides and get secant squared theta minus 1 is equal to tangent squared theta. And of course, we can get secant squared theta minus tangent squared theta is equal to 1. And all of those are going to wind up being not only useful or capable of being used to find values when we're evaluating the trigonometric ratios as we're looking for them for any particular value that we're given. They will come in hugely in the next section when we deal with analytic trig. But notice that all three of these and their two variations come from basically the Pythagorean theorem, right? It comes from side squared plus side squared equals hypotenuse squared. And that's, of course, why they're called Pythagorean identities. It's almost like they name these things on purpose. Alrighty, let's go ahead and look at what are called the cofunction identities. Now, cofunction identities, again, are intentionally named. And I bet you're wondering, I'm curious what that co out is in front of there. Well, have you ever noticed that there's sine and cosine, tangent and cotangent, secant and cosecant? Well, there has to be a reason why they actually name them like that, and there is, okay? Let's say that I have, this is my theta right here, okay? If I want basically the sine of this, I know that sine theta is going to be opposite over hypotenuse. Well, let's go ahead and rename these because I'm about to do something fun, okay? A, B, and C. Okay, so opposite becomes A over C. Now, remember that the sum of all the angles in a triangle have to add up to 180. And if this one's a right angle, then these two remaining angles need to add up to 90 degrees, or pi over 2. Okay, that means that if this one is theta, this one has to be pi over 2, or 90 degrees, minus theta. It has to be the difference. It has to be what's left, because you have to be able to add those two together and get pi over 2, or 90. Okay, so what is cosine of pi over 2 minus theta? This angle. It's going to be the adjacent over. It's going to be the adjacent over hypotenuse. It is exactly the same ratio. The co stands for complementary. because this angle right here is 90 degrees, the two remaining angles are complementary. Sine of an angle is equal to the cosine of its complement. Okay, and the same is true for secant and cosecant, tangent and cotangent. Okay, let's just go ahead and let's say that we have tangent of theta. Tangent of theta, of this theta right here, is a over b, right? What do you suppose the cotangent of its complement is? Well, it's not going to be opposite over adjacent, it's cotangent. It's going to be adjacent over opposite, and that's a over b. And it has to do with the necessary relationship between these two angles right here being complementary, because 90 degrees is taken up by the right angle down here, creating the right triangle. Okay, and so up here I've put the cofunction identities in terms of pi over 2, and I've gone ahead and just relisted them down here in terms of 90 degrees, but they communicate the same thing. Sine of an angle is equal to cosine of its complement. Cosine of an angle is equal to sine of its complement. Secant of an angle is equal to cosecant of its complement. Cosecant of an angle is equal to secant of its complement, and so on and so forth. Okay? Now, I'm hoping that that was just tons of fun. Okay? Because what we're going to do in the next video is we're actually going to start working some problems based upon the definitions and the identities that we've explored up to this point. Okay, I'm going to go ahead and stop this video right now because it seems like a wonderfully logical place to go ahead and stop. But the rest of the videos, and there will probably be 2 or 3 depending on how quickly I can actually get through some of these problems, is largely going to be working out practice problems based upon our knowledge thus far. Bye, guys.